Okay, let's get started with the last one, I believe. This is going to be probably separated into 3 parts, so let's get started. Just going to go over some terms to know, but that's probably going to be my next slide, just other stuff. For the sake, I'm going to just start with going through a quick understanding of how acid and bases work. So, an acid and bases use a pH scale. This pH scale goes from 0 to 14. If your pH scale is 7, or your pH is 7, that is a neutral pH. And usually this is going to be found in your water. Your acidic side is going to go to 0, so 0 to 7 is acidic. And 7 to 14 is a basic, or a base. We can understand them a little easier by knowing that an acid will donate a proton, or donate an electron, and it is usually figured out by its H+. A base will receive an electron, and it is understood by its OH, or its hydroxide. Very very easy to grasp. Just, I don't think it's gonna ask you about anything really hard with acid and bases. I think it's just gonna say if it has a pH of this, what is it? Basics, acidic, or what does it release, or does it get a proton, or I mean get an electron, all that. Just the common stuff. So now we're gonna talk about atoms, numbers, and the JAG, the Lewis base structure, maybe even. So the smallest particle matter is an atom. So yeah, and there's 100 types of atoms, and these atoms are called elements. Now, an atom has multiple structures, so I'm going to say that I'm going to have this be my, so let's say we're doing an atom for oxygen. Oxygen has 8 protons, so 1, 2, 3, 4, 5, 6, 7, 8, and it has 8 neutrons. So this is my atom right here, or this is my nucleus. But we're not done yet because we still have our electrons. So 1, ignore this, it's really bad. So now we have 1, 2, 3, 4, 5, 6, 7, 8. Where these red circles are my electrons, these green circles are my neutrons, and the blue circles are my protons. So this in the center is called your nucleus. And these little shells, they're called orbital shells. These orbital shells are called your electron cloud. Because while they look like a ring, they're really just a cloud. And they have levels. And they move really fast, so it makes it appear like it's a cloud. Chemically bonded chemically bonded groups of atoms are called molecules. Molecules are like so. They look like this. These are chemically bonded atoms, and they could be different groups. So this is also an atom, O2, because it is 2 atoms combined together to make a molecule. They can be made up of a lot of molecules. They can be made up of a lot of atoms, not a lot of atoms. It's anything that really just combines together is an atom. When an atom loses or gains an electron, it becomes a positively or negative charged atom. And so if it loses or gains an electron, it is called an ion. And with acid and bases, these are ions. You can tell if it has gained or lost an electron because if it is negative, it has gained an electron, and if it is positive, it has lost an electron. Let me erase this. So the structure that you saw is how they usually look like. I'll just go ahead and explain real quick what a Lewis-based structure is. I don't think it's very important, but if you are given a question and you're trying to see if, like, how much electrons are given, maybe it helps to understand how it works. So I'm going to use CO2 real quick. It has 6, right? It has 6. Yeah, it has 6. So 4, 6. Or really, it'd be like this. So it would actually look like. So think about this is the understanding, which we'll talk about later, is that this is a covalent bond because they are two nonmetals. I believe, yeah, covalent. It's a covalent bond. And the thing about covalent bonds is they're going to share electrons so that they all reach 8. Um, so this, they can only share, you can only share an electron 3 times, which is a triple bond. You can share 2 times, which is a double bond, or 1 time a single bond. And this is just how much electrons is being shared between these atoms. For example, if I were to have, I would like to share this electron with this one, and oxygen with this one, and same for this side. So what we would do is draw it like this, because now this is considered 2 electrons, 2 electrons, 2 electrons, 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 8, and 8. This is what structures usually look like if you're ever confused on how many electrons is shared or who's losing the electrons. If it is a covalent bond or a non-metal bond, don't be afraid to draw the structure out and see what you can pair up together. Because not everything can be paired, but some might. So that's just a little understanding of that one. Nucleuses or neutrons have a charge of 0. Protons have a charge of 1, and electrons have a charge of -1. So usually if it's a neutral element, there's going to be the same amount of electrons for the same amount of protons. But just because there's the same amount of protons, same amount of electrons, if you're not given enough information regarding how much protons and neutrons and electrons are in the atom, always know that the proton will always be right. Because you can't change a proton without changing its entire atom. But you can change an electron and its neutron, and the identity of the proton, the element stays the same. So we went over that. We also went over that. I guess we'll talk about this last slide about for atoms and numbers. So the electron configuration. Y'all have seen what I did with the clouds and stuff. My bad. So y'all see what I did with the electron clouds. There are shells, which I'll just right here. So this is a shell, 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 and it gets bigger and bigger and bigger the more protons there are, because protons are the same as electrons. And the amount of electrons on the shells can vary a bit. And it's like hard, I guess, to explain in my best ways, so I don't really think this is important that much. I don't think this will be really on the test, but something to note is that elements on a periodic table, I believe these are called periods. Let me see. Is that what it's called? Up and down is vertical. So no. So the verticals, which are called columns, elements that are in the same column will have the same valence electron. Valence electrons are your most outer electrons in the most outer ring. So if I did nitrogen, nitrogen has 7. So 1, 2, there's our nucleus right here. 3, 4, 5, 6, 7. So nitrogen has 7 electrons, but if I were to ask the valence, it only has 5 valence electrons and 2 inner shell electrons. But what if I asked you, or what if the thing asked you, where's this periodic table? What if I asked you, what about phosphorus? Now, phosphorus has 15. Wait, that's 15, right? Yeah, phosphorus has 15 protons. So if I were to draw it again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, another one, 11, 12, 13, 14, 15. It just has an extra shell, but the valence electrons stay the same. So anything in the columns are going to have these same valence electrons, no matter what. This is very important because they are grouped kind of based off of their reactivity. This valence electron determines that reactivity because it determines do they want to become a full shell or not. And in this case, nitrogen and phosphorus both want to be a full shell, so they're more reactive than, let's say, calcium, which only has 1. So yeah. Elements, we're going to keep going. Elements cannot, they're the most simplest form that can't be chemically broken down. Compounds is made of a tumor. Elements, they're chemically bonded, and they kind of, I don't know if they can. Let me see. I don't believe they can be broken. No, yeah, chemical compounds can't be broken down. My bad, because you can break down a lot of stuff. So an example is like glucose, which is sugar, which is CHO. We also have formaldehyde, which is CH2 oxygen, and like other things. So these compounds will have the same elements, and something to take notice is they all, not all, but these two actually have the same ratio. So this one has a 1, 2, 1. This has a 1, 2, 1. Just a little thing interesting, but you can make the things are made up of the same elements usually. It's going to be your more natural ones or your organic compounds, but their ratios will be different. Therefore, what they do is going to be different. A mixture is made up of tumor elements, but a mixture can be physically separated. So these are compounds. You can't separate them, not without a lot of struggle. A mixture can be made up of 2 things. These are like physical, 2 common physical separations are going to be like filtration and evaporation. So like gravel and water or salt and water, which can be separated by evaporation. Mixtures can then be separated into 2 further types. So homogeneous, I'm bad at words, and heterogeneous. That's right. So homogeneous are going to be uniformly separated. So this is going to be when one of the components is usually liquid, which is going to be called the solution. And the other one is going to be called the solvent. Yeah, it should be the solvent, which is usually going to be the one that is being dissolved. Oh, so these, a good example is salt water, sugar water, those little packets that have like the Kool-Aid powder in it you put in water. Those are homogeneous solutions, but heterogeneous solutions are not evenly mixed out. Samples can be taken from the heterogeneous to show a variety of ratios. An example of this is gravel and water, because you can take out gravel in water. And the ratio of how much gravel and water is different, it's not the same, which makes it a heterogeneous. So mixtures are usually for more physical properties, and compounds are usually for more chemical properties. All right, so the next one is going to be categories of states of matters. I'm not even going to say it. There's going to be 5, but we're just going to go into detail about 3. So we all know what a solid, liquid, gas is, and they're determined by the energy molecules that make up the substance. So at lower energy levels, molecules are more likely to go into a stricter position, and they are less likely to move around, which makes them stable in that solid state. Which gives them that fixed volume and that fixed shape. Solids can't be compressed. You have your liquids. Your liquids are going to be usually having a little more energy than solids, which give them more flexibility to move. Therefore, they don't have a fixed shape. They just take up the shape of their container. But they don't have enough. Liquids don't have enough energy to change their volume, so they still have a fixed volume and they can't be compressed. But gas molecules are really fast, they have a lot of energy, and they're not held together by their bonds. They can move freely and spread out against the space, and for this reason they don't have a fixed shape and they can be compressed. But this is where you get into that specific gas laws and all that junk, so. What about the relationship between matter and energy? So, I'm going to just write this, law of conservation of mass. So, as we know, all matter cannot be created or destroyed. It can only be rearranged or transformed. So, what this means is basic elements can stay the same, but compounds can be broken or rearranged into other items or other rearrangements. So, like if you were to burn a log and you get ash, it is going to seem like something was destroyed, but that ash is still the log. It was just burned, and now half of the atoms in that log got released into the air in the form of carbon dioxide, while the other got stuck into the solid form of ash. We're not going to use this. That's a really bad equation. Now, there's also another thing called the first law of thermodynamics, which is the conservation of energy, which means energy, which is the same as mass, cannot be created or destroyed. What this means is if you were to hold an ice cube in your hand, because your hand is hotter than the ice cube, your hand is going to release heat, and this heat is going to cause the ice to melt. And so, what people think is that, okay, well, the ice cube released its coldness. Well, you can't release cold, you can only release heat, really. So what this means is that you lost heat from your hand, and the ice gained heat from your hand, which means it's heating up. It's not getting colder. It might feel like it's getting colder, but really, it is sucking in heat, which is releasing cold air. If you were to release hot air, it is sucking in cold air to release hot air. We're not going to go over that too much. There's common forms of energy, so I'll just write them down, but they're not really important. The main ones I think is chemical, thermal, chemical, okay, so chemical, thermal, mechanical. I think those are the 3 main important ones to know. But what about kinetic and potential energy? Erase this real quick. So chemical and okay, so chemical and electrical energy or kinetic and potential energy is just it's just the energy of movement. So kinetic energy is the energy of movement, and potential energy is the position or the energy of position. So what this means, so if I were to do this, and this is the roller coaster right here, this is potential. This is potential energy. It hasn't went yet, but if the roller coaster was down here and it was zooming, this is kinetic energy because it is moving. Potential energy is the energy that it can have based on its position. Now, I'll just write this down. When I was taking the test, I didn't really see anything worth this, but in case you want to just know, this is the formula, which M stands for mass, V stands for velocity, and the formula for potential energy is just mass times the gravitational force and height of the position. Like I said, I don't really think this is important, but maybe this one is. So if you were to ask your total energy, which is T, you would just add your kinetic energy plus your potential energy. It's pretty simple. This one's probably the easiest one to grasp. Alright, next one is just to understand a little bit more about thermal energy. So, there are three types of ways you can, I'm going to go over this quickly. I don't want to make it very complicated. So there's three types of ways you can transfer: conduction, convection, and radiation. We're all really familiar with radiation. This is going to be in the form of your electromagnetic waves, so like your UV waves. This is the only type of method of transferring thermal energy that doesn't require matter as a medium. So what this means is, like, if we were to use conduction, we use a medium, so it's something solid versus something solid. So like a hand, this is a hand by the way guys, a hand and an ice cube. And the ice cube is melting because of that energy is getting transported between both of them. Convection's a little different. It's just going to be more of a liquid solid state or liquid gas state. Liquids, the molecules in liquids are always touching, so heat transfers rather quickly. But molecules and gases come into contact with each other, but they're not in constant contact because they're moving around, so they kind of change a little slower. Using a fan is a really good way for people to transfer heat in the gas really fast. But I mean, I really wouldn't worry too much about this convection, all that junk. Okay, so this is so bad. Okay, so we're gonna go over this really quickly. We're gonna have to tell you about the specific heat capacity, which is considered S. The specific heat capacity is the amount of heat that is needed to increase the temperature of 1 gram of material by 1 degree of Celsius or Kelvin. Very complicated, big word, but just know, I guess, because even I was struggling trying to understand it. It's just like how much, it's just how much heat you need to raise the temperature of an entire kind of solid based on just 1 Celsius degree or 1 Kelvin. If you have the specific heat, you can use this formula. And this is delta T, which means just a change, so it'd be the change of the original minus the new. Or I think new minus original. It's just a change. So Q just is the amount of heat transferred, S is that specific heat we talked about, M is the mass, and this is just your change in temp. This whole process is called calorimetry, which is the technique of measuring the amount of thermal energy transferred. There's a lot of ways you can use this. I'm not going to tell you all the ways, so you just need to know that what calorimetry is. It's like something you do in the chemistry lab, so. Now, there are three types of temperature scales, Kelvin is going to be your best friend sometimes. But Kelvin is usually found by your degrees Celsius plus 273.15. This number is constant no matter what. To go from Fahrenheit to Celsius, you just are going to go 5/9 and then your degrees Fahrenheit minus 32. And to go from Celsius to Fahrenheit, you're going to do the inverse. So you're going to do Fahrenheit equals 9/5 Celsius. So you would multiply the Celsius by 9/5 first plus 32. And these are just the three ways you can find this. Oh my god. Okay. I feel like I skipped by rays and went straight to heat, but it's okay, I'll go back to rays. So, there are other laws, the law of energy. I don't really want to go over it, so I don't think it's that important. But what is important in your changes of phases is chemical versus physical changes. Physical changes don't involve chemical compositions of matter changing, so if the physical property changes, it is a physical change. So what this means, solids to liquids to gas. Does it melt? Does it freeze? Is it condensing? Participating? Precipitate, I think. Condensation. Stuff where the property itself stays the same, it just shifts through a phase change. Chemicals, on the other hand, have a chemical change. So rusting is a chemical change. Molding is a chemical change. Burning is a chemical change. And this is because when you do this rusting, molding, burning, there's a new chemical formula or a new chemical compound coming into play. You're losing a chemical element. They are much permanent. Some of these you can't revert. You can't revert burning. You can't revert molding. You can't revert rust. Like you can, but you really can't. And so they're different because these atoms have to be separated with other elements to be different objects. So, like my rule of thumb is burning. If it says burning, molding, or rusting, it's chemical. That's pretty much all you would have to know about this one. Alright, so we just have a couple. We're just gonna go over this one thing, and then we'll go over bonds. And I don't know about rays. I don't know why I put rays, but oh well. So I'm just gonna go over what is called the electromagnetic spectrum. Okay, I ran out of space. Yeah, I did gamble too big. So what this is in electromagnetic spectrum. What this is basically talking about is the high energy. So your gamma rays are going to have the most energy, and as you get further down to radio waves, they get less and less frequent. They get less and less intense. So in terms of frequency, understand that frequency increases that way. So frequency and your wavelength goes inversely related. Oh shoot, I spelled that wrong. I spelled that so wrong. It's okay. I can't. I'm tired. I'm too tired. I'm just gonna erase that. We don't even gotta see that. I'm going to just write the appropriate sign then. So, visible light is the light that we can see. It's those colors that we know. And as it depending on what it asks, the question might ask, what is the smallest frequency wave? And you would say radio because it has the smallest frequency, or it might say rank these based off of, like, out of all these, which one has the lowest wavelength? And you might not have gamma ray, you might have UV visible, micro, and radio, and you would have to say UV because UV would be the lowest wavelength out of all four, options given. Other than that, this is just understanding like where they go and stuff like that. I don't really. I know there are a couple questions. There are going to be a couple energy questions on the test. Maybe not the test I put, but just in general. I think energy is one of those things where like they for some reason like to talk about energy a lot. Let's see. So we're gonna go over bonds real quick. We're gonna skip rays, I think. I don't think. Well, rays is basically the gamma rays, X rays. That's what rays are. So I guess I did go over it. But we're gonna go over bonds real quick. There's two types: ionic, covalent. So an ionic is going to be your metals plus nonmetals. And your covalents are usually going to be a nonmetal plus a nonmetal. So what this ionic means is NaCl, which is table salt. This sodium is a metal, and this chloride or chlorine is a nonmetal. But if we were to do, let's use CO2 again, this carbon and this oxygen are both nonmetals, which is different. So the reason why this is different is because covalent bonds are going to share electrons, which I already showed you how they shared it with the little dashes of uh the little dashes, which this bar signifies a sharing of electrons between both elements involved. If you were to do like it could literally be anything, like you could have one that looks like this. This is a type of covalent bond too, which would just be what, CH2O or something like that. So they're pretty they can be made in different ways, but these are all types of covalent electrons. The reason why ionic bonds are a little different is because sodium, what this means is because sodium has 1 electron, valence electron, and chlorine has 7. Why the heck would chlorine just share all 7 electrons when it can just take sodium? And why would sodium want to get 7 electrons when it can just release 1 and be having double gas? So that's what they do. This just gets taken over there, which leaves sodium by itself. And what happens is because they lose this electron, they drop a shell down, and now it's technically, they're both full shells. So usually they're just made between a nonmetal and a metal. Ionic bonds take away electrons. One takes and one gives. And covalent bonds are nonmetals and nonmetals, and they both share electrons. I don't think that there's anything else I should have to explain. I weirdly think I got all of it in the first slide. Um, I mean, I'll go to the next one because it's supposed to be science anyways. And, like, I think I did pretty much everything. Like, I talked about matter, which, matter can never be created, destroyed, or, can only be transferred. I talked about that. Yeah. I'm all over the place. I apologize. It's just weirdly a lot. And it's only like 10 minutes, so it's weird. I talked about matter a bit, so just the volume and mass. I talked about that atomic structure. I talked about how you can classify elements into compounds and mixtures, how to categorize. I talked about the relationship of matter and energy, and also, I don't think radioactive materials are important. I mean, I would go over it, but I genuinely didn't see it on the test. The test on the book, I didn't see anything about radioactive. I do know that there are questions on this test that I didn't talk about, so I'm gonna go over it in the physics portion because it should be small, like a short short physics, and then I can spend more time talking about it. I talked about the movement and energy. So movement and energy is just like what I think solid, liquid, gas, just all that jazz. There's not really much else to talk about. I think I went over a good portion of it. So in the next one, we'll be going over chemistry, and it's just one slide of chemistry. We're just going to talk about a little bit of periodic trends and stuff like that. So that should be it for this one.